Study Unit 3, Lecture 3. This lecture and Lecture 4 focuses on the driving of transistors and thyristors. Lecture 3 will specifically focus on transistors, and Lecture 4 will focus on the driving of thyristors. Power MOSFETs and insulated gate bipolar transistors are voltage control devices. In other words, a voltage needs to be applied to the gate in order to turn the device on. In the simple example here, when the applied voltage is 0, or when the device is off, then the impedance between the drain and the source is very high and very little current will flow. When the device is turned on by applying a voltage larger than the required gate source voltage of the device will turn on by forming a conduction channel between the drain and the source, and current will be able to flow. This lecture takes a look at different types of circuits which can be used to apply the appropriate voltage at the gate over here in order to turn the device on effectively. The reason there are multiple circuit types for driving the gate of the transistor is because the transistor is not an ideal device, and there is a parasitic capacitance which exists between the gate of the transistor and the rest of the device, and it is this parasitic capacitance which must be overcome in order to turn the device on effectively. The primary differentiation between the different driving circuits are the circuit's ability to drive current to make up for this parasitic capacitance which is present on the gate of the device. The different driving circuits also have associated switching speeds associated with those circuits, where there will be faster circuits and slow circuits. So the transistor that will be used to demonstrate various examples will be a trench gate N-channel enhancement mode power MOSFET shown here. The advantage of this type of transistor is that it has a reasonably low threshold voltage, which means that it can easily interface with logic level circuits, particularly TTL level circuits. So shown here are several example circuits from the reference material on different ways which the gate of the device can be driven. So in the first example, the gate of the device is directly driven from the CMOS output of some logic inverter. This approach is quite convenient because the CMOS logic inverter is relatively easy to control and interfaces well with other controlling electronics. A problem though is that these types of inverters have limited current sink and source abilities, so the type of rise and fall times which can be expected at the gate of the switching transistor will not be that great. The reason that these gates have limited sink and source abilities is because they are designed to run other gates. And although this device, or the transistor power device, is able to accept the logic levels, it requires larger currents from the driving device in order to get appropriate switching rise and fall times. The switching speeds which are associated with using CMOS logic gates to drive the power device can be improved by running multiple inverters in parallel as shown here. This effectively increases the ability of the inverters to either sink or source current. In circuit B, the switching times are improved by using BJTs in the emitter-follower configuration. In this example, instead of using the logic to drive the gate of the power device directly, the logic switch is instead used to drive the base currents required to operate these two bipolar transistors. These bipolar transistors are in emitter-follower configurations, which means that now the switch time is no longer limited by the current sinking or sourcing abilities of the logic gate, but instead by the capabilities of the bipolar transistors used. This type of circuit is effectively a current amplifier, where this logic gate over here will either turn this transistor here or this transistor here on in order to generate the currents required to compensate for the gate capacitance present on this device. The reason this circuit speeds up the switching time significantly is because the current provided by the CMOS gate is effectively multiplied by the beta of the BJT transistor, which then supplies that current to the power transistor. The primary advantage of this circuit is that the switching timers are now no longer limited by the CMOS logic used, but instead by the specifications of the BJT transistors used. Example C here is sort of a hybrid of these two, where example A and B made use of CMOS logic. Example C uses TTL logic to drive the gate of the power transistor. TTL devices make use of what's called an open emitter, and this allows the output drive of this TTL gate over here to sink an incredibly large amount of current relative to the CMOS counterpart. However, this configuration has very limited ability to source current into the CMOS gate. To compensate for the limited ability of the device to source current to the power MOSFET, an extra resistor is used in this configuration, which allows additional current to be sourced directly from the power supply into the gate of the power transistor. In this configuration, when the input of the power MOSFET is being driven low, then the current sinking ability of the TTL gate will be an advantage, as the current will be sunk through. When the input of the power MOSFET is being driven high, then this additional resistor provides an additional current path for current to not only go through the TTL gate into the main power supply, but also through the resistive element into the power supply, thus increasing the ability to sink current, or rather source current, into the device. Primary disadvantage with this type of configuration is that TTL logic is limited to 5 volts, so if larger voltage is required to operate the entire switching circuit, then another solution is required. The voltage limitation can be overcome by making use of an additional external circuit which will effectively shift the driving voltage to whatever the desired voltage is. So in this example, the TTL output of the logic gate has a 5 volt limitation, but with the addition of this emitter follower BJT over here, the output level can be lifted up to 15 volts. In this configuration, whether the power MOSFET is on or off is still determined by the output state of the driving circuit, but the additional BJT circuit here allows for the output level to be shifted to a higher voltage than is required by the TTL logic block. In example E, the power MOSFET is once again driven by a CMOS inverter, but the supporting circuitry around the inverter has been augmented with 2 capacitors. The purpose of these capacitors is to store additional energy, which allow this circuit to source additional current during the switching period. So for example, this type of configuration can typically source about 1.5 amps in a few nanoseconds. In example F, the switching circuit, or the circuit which controls the state of the power MOSFET, is electrically decoupled from the switching circuit itself. In this example, there is an optical interface between the switching voltage rail and the power voltage rail. The advantage of this configuration is that very fast rise and fall times can be achieved by having the appropriate drive circuit, and this circuit will be controlled optically from control circuitry. In this way, the control circuitry is not responsible for providing the sink or source current required to quickly switch this power MOSFET on and off. Furthermore, this optical interface means that level shifters such as the one used here are not required to drive the gate. Thus far, the switching circuits shown have been very simplistic, with a single power device with a single load or resistor representing the load. What is more often the case is that there will be multiple switching devices driving a single load, such as an example G here, where there are 2 power MOSFETs driving a resistive load. In this example, current will be sourced by the N-channel device over here, and current will be sunk by the P-channel device here, and these 2 devices will operate in tandem in order to provide current to the load. Each device, however, does require a different driving circuit, even though both driving circuits will be run by the same switching signal Q. The N-channel device is driven by this known emitter follower configuration over here, which simply uses 2 BJTs to provide the required current to compensate for the gate capacitance on the N-channel device. The P-channel device is driven by the complement of the switching signal Q and requires a resistive bridge and a level shifted emitter follower circuit to provide the currents required for the P-channel device. The resistive bridge over here, R1 and R2, is for controlling the base voltages of these transistors, but what's important for this circuit is that the BJTs used are able to withstand the total supply voltage at this top rail Vs. If the breakdown voltage of the bipolar devices is not in excess of the supply voltage used, then this type of configuration will not be suitable for driving the resistive load RL. In this example over here, the source of the power MOSFET is not referenced to ground. This device can still be driven by making use of an additional switching transistor and a transformer. Specifically in this scenario, this is called galvanic, which is just really electrical isolation, and this type of transformer in this configuration is a pulse transformer. The reason for that is because the switching state of this MOSFET is driven by a train of pulses representing on and off. When the device turns on, The parasitic diode present in Q1 allows for forward conduction path to charge the device and will keep it so until a negative pulse turns on Q1, allowing this device to discharge and thus turning off Q2. Finally, example I is another example of using optical isolation to control the TTL gate, which drives the input of the power MOSFET. All these different switching circuits can be categorized as either high side or low side circuits. Low side circuits are where the switching circuit is at more or less the same potential as the output driver or the supply rail of the power MOSFET being driven, whereas high side circuits are circuits where some other level shifting is required between the switching circuitry and the actual power switch. In all these examples, the voltage or the clamping voltage at the gate is either 0 and 15 volts or 0 and 12 volts or sometimes 0 and 5 volts. And this is a problem because very often, for noise immunity purposes, the switching voltages may vary between plus and minus 15. In other words, the switching signal might vary from plus 15 volts to minus 15 volts and passing through 0. Because the controlling signal might vary between a negative and a positive voltage for noise immunity purposes, it may sometimes be required to have a driving circuit which can accommodate a negative switching voltage. The circuit shown here makes use of two techniques to drive the two power transistors. One is a charge pump circuit and one is a bootstrap type circuit. In the charge pump circuit, the transistor CP for charge pump, is successfully charged and discharged through diode DCP1 and DCP by rapidly switching the switching transistor over here, TCP. So when the capacitor discharges, it will discharge through DCP, and when the capacitor charges, it will charge up through DCP, and whether it charges or discharges is dependent on the polarity present on this side of the charge pump circuit. So in other words, when the transistor is on, current will be able to flow and charge the device. When the transistor is off, no current will be able to flow and this capacitor will not be able to charge. Whether or not TCP will discharge or not is dependent on the state of CGS, where CGS represents the gate voltage supply capacitor. This means is that if the voltage here is low, then this diode will be off and current will not be able to flow, and the current or the charge which is stored in CCP will not be able to discharge through DCP into CGS. Moving on to the diode bootstrap part of the circuit. If switch TL1 and diode DL1 are conducting, then it is possible for charge to flow through the bootstrap diode DBS here, through CGS, and down through the conducting path to ground. This allows this capacitor here, CGS, to charge up. When the lower transistor diode pair are not conducting and the upper switch and diode are conducting, then this will reverse bias the bootstrapping diode and current will not be able to flow to CGS. This means that the high voltage required to switch transistors is supported through the charge pump circuit and these two diodes over here, which provide the VGG required for this gate. In combination, this allows a higher voltage to be supported over here, which is higher than the total supply voltage plus the required voltage for the buffer driving the top switch. The reason that these two circuits are used together is that startup is a problem when only using the bootstrap technique, and the charge pump circuit is required to provide a startup condition for the top switching transistor. This concludes this lecture. Lecture 4 will have a look at techniques which can be used to drive thyristors.